Find the largest couple that we can apply M before we have motion. And here we're told that the disk is 45 kilograms. And friction between the disk and the ground, 0.2. In our free body diagrams then, I have the connecting rod between C and B. And then I have the disk also that I have to model here. So acting on the rod, I have a pin connection at C and a pin connection at B. And I'll assume that both of them are up and to the right. And on this connecting rod, this is where I'm exerting that force M as well. And that's everything happening to my connecting rod. I have 5 unknowns attached to it. So my second picture, I have what's happening to this disk. It's 125 millimeters in radius. It's connected to that point B, and like we saw before with our frames and machines problems, I already said B in this picture was right and up. So I'm obligated to say that it's left and down in the matching picture. Let me put the weight first. My weight, it's a mass of 45 kilograms, so it's going to have a weight of 441 newtons. And at A, where I have that contact, that's where I have a normal force from the ground. And there will be friction between these two surfaces. And this is where we have to say, in what direction should that be going? So if we are, and we could presume wrong, it's not necessarily always obvious. Will it want to rotate one direction or will it want to rotate the other direction? So in this case, if we're applying M in that direction, what direction would we think the friction is going to go at point A? Right, it seems like it should be going to the left because we're pulling this rod down and it's going to be trying to move the disc towards the wall, we would think. So it appears as though it goes to the left, but the math will tell us if that assumption is right or wrong. And if it turns out that we get negative friction, that would mean we should try this again, but now draw it to the right and then resolve it. So you don't have to know ahead of time what's happening, but you have to verify that your assumption was right by getting all positive normal forces and all positive friction forces. So it does appear here that it's pointing to the left. Those are all the forces acting on the disc 2 and all the forces acting on the rod 1. So we can now use them to write our equilibrium equations as we've been doing. This is a rigid body at 1, and this is also a rigid body for free body diagram 2. So we'll get 6 equations out of this. We're going to have 5, 6, 7 variables, though. Yeah, I'll reiterate, we can't treat this as a two-force member because we have a moment acting on it. We do know that these are going to be equal and opposite, these are equal and opposite, but we don't know its direction. So we do have to do the full free body diagram on this. So Cx is negative Bx. And Cy is negative By. But we see in the moment equation where it starts to kind of throw things off. If I take the moment around C, this is where we want to use that rule of thumb. We have a pin at C and a pin at B. I'm better off taking the moment about a point that only appears in one picture. So point C is just a little bit better to take the moment about. I have my applied couple M, which is going to be counterclockwise, minus, and I converted to meters for this equation, 0.3 times by plus 0.4 times bx. Yeah. I have 5 unknowns and 3 equations, so I'm going to just put them aside and kind of carry on with writing more equations here. Looking at picture number 2, if I sum forces in the x, I'll get my negative bx minus fa. Again, I'm presuming that it wants to slide to the right, so fa is pointing to the left. In my y direction, I'll have minus by plus na minus 441, the weight of the disk. Again, here's an instance where the normal force of A is not simply the weight of the disk, because however much that rod is pushing the disk into the ground or possibly lifting it off the ground is going to affect the value of that normal force. So Na is not going to be 441 newtons. And if I take the moment around point, it doesn't have a name yet, so I'll call it point O. The weight force will not affect that. The normal force will not affect that. They both act through the diameter of my disk. Bx will also not affect it because it's going to have its line of action pass through O. By, though, will. The way I've drawn by down, it's going to be then a positive 0.125 times by. Again, I'll convert everything to meters for this. And I have the friction force, and that's going to be a negative 0.125 times Fa. Looking at how I have my equations so far, I can't get that normal force Na easily because I have 6 equations and I have 7 unknowns, and there's a different collection of variables in all of my equations. Here I have a Bx and Fa. This has an Fa and a By. This has a Bx, By, but that has an M in it. So it's not really looking obvious yet of how I can go about solving this. But these are the 6 equilibrium equations that I can get out of these 2 pictures. Again, 7 variables, though, for these 6 equations. There's only one, or we can only come up with initially one way that this is going to move. We think that the disk is going to slide to the right, which means that if it's going to be slipping, and we want to see what's the maximum M we can apply before motion occurs, as we've been seeing before, we're going to presume that that friction force is maxed out, and if we twist it just a little bit harder, it would then actively be sliding to the right. So this, not coming from my equilibrium equations, I'm going to say Fa is maxed out. It's mu times N, so it's the 0.2 times Na. We're still, again, operating under the presumption that it wants to slide to the right. That could be disproven if we were to come out with a negative friction force, which we don't know yet because we don't have numbers at the moment. But if we look, we do have 7 equations, and we have 7 unknowns here. So if we put this into MATLAB or Wolfram, I'll let that do the algebra, but I get that M has a value of 77.2. I converted these to meters, so my M is going to come out in newtons times meters there. I don't remember what the number was, but it is important to verify our assumption. I do know for a fact, though, when I looked at this, that Fa was greater than 0. So Fa was positive.